So now I just wanted to go a little bit more into rotational momentum and then how it ties in with torque right here. But first, I want to look at another collision between a stick and a ball right here. So this stick is just floating out in space. I don't want it to be tied with gravity or anything like that. It's just floating out in space. And we're going to throw a ball and hit it right here. And it's not going to stick right here. Matter of fact, it'll be an elastic collision right here. Then afterwards, this ball will, even though they're the same mass, this ball is going to continue moving forward. This stick will be moving forward, plus it'll be tumbling right here. And so what we'd like to do is we'd like to find out how fast this thing's moving after the collision, how fast this is moving, and how fast it's tumbling right here. So we say an object of mass m collides with a stick floating in space. The stick is originally at rest and is hit at the end. We hit it right at the end. The collision is elastic. The mass of both objects are m. Find those three things. Find the speed of this afterwards, the speed of that one, and the amount that it's turning, given this initial speed and the length of the stick right here. Now, first of all, we can use regular momentum on this. Why? Because the only forces on this thing is whenever this hit it, there's a normal force there and there's a normal force back, and we're looking at the entire system. So the total force is 0, so we can use regular momentum. So we'd say all the momentum in the x. Well, before it's just mv naught. Afterwards, this is still moving horizontally, so it's mv prime, plus this is moving horizontally, so that's mv center of mass. If this thing were to be pivoted right here at this point, so it went like this, we could not have used momentum because there would be forces on the pivot point up here, the pin. Okay, now we can look at angular momentum right here. We're going to look at angular momentum about the pivot point, the middle, this thing that's spinning. Well, before, this thing is moving in a straight line. So remember, angular momentum when you're going in a straight line is your momentum times your distance. So it's mv naught times L over 2. Then afterwards, it's still going along this line. So it's still m, but it's v prime times L over 2. Plus, this thing is turning. He's got I about that point, which is 1/12 ml squared times how much he's rotating. So there's the angular momentum right here. We cannot, here I wrote down, we cannot use the relative speed equation. That was only for regular momentum. There is no rule for relative speed here. Okay, so now we can, since we said it was elastic though, we can say the energy is the same, the kinetic before and afterwards. So here, you just have 1/2 mv naught squared for that one. This one, he's just moving in a straight line, it's just 1/2 mv squared. But this one is moving and turning. So he's got his, due to this movement, he's got 1/2 mv squared. And then he's rotating, which is 1/2 I omega squared. I cannot say V equals R omega because this omega has nothing to do with the speed right there. Okay. Well, so now all I have to do is, first of all, I said cancel the common terms. Well, they all have 1/2s in them. They all have m's. I can cancel the m's out of this. I can cancel the m and a 2 out of this. So this equation up here just becomes V naught equals V prime plus V center of mass. This equation right here, I canceled an ml over 2. So this just became V naught, that just became V prime, and that became 1/6 L. And then from this one I canceled the 1/2 m's, and so it just came out to be that equation right here. So I said, let's take the V center of mass right there and plug it into here. And let's take the omega prime from this equation and plug it into here. And we'll solve for V prime. So if we do that, we get V naught, if we plug it in here, we get V naught squared equals V prime squared, And in place of the V center of mass, it's V naught minus V prime squared plus, and then over here, we got solving for omega prime. We'll put that over here. It's going to give me a 6. We're going to square it, which gives me a 36 over 12, which gave me the 3 V naught minus V prime. Or I squared it all out and canceled the terms right here, and I came out with this quadratic right there. 5V prime squared minus 8V naught V prime plus V naught squared equals 0. Solving for the quadratic, it was 8V naught plus or minus 2V naught over 10. Now I know it couldn't have been the plus, because if it was the plus, that would be V naught. And I know that that speed has to be slower than that speed. It can't be the same speed, so it has to be the minus right there. So 8 minus 2 is 6/10 or 3/5 right there. So this thing's going to be moving at 3/5 of that speed. V center mass, then I can come up here and plug it into here. We know that's V naught, and we know that's 3/5, so that must be 2/5 right there. And then we can go ahead and come back and plug it up into here. We know V prime, and we know V naught, and we can solve for omega prime, and it just came out to be 12 V naught over 5L. So we got how much it tumbled, how much the stick moved, how much the ball moved afterwards right here. Okay, so this is probably the most difficult stuff we'll do in the class, this ball and a stick right here, right? But now I'm going to go back and remember, Newton's second law was the sum of the forces is the change in momentum with respect to time. Well, if we just convert that to our switching our letters, it also says the sum of the torques is the change in angular momentum with respect to time. So, in these two, an equation has to have the same direction. So the direction of the torque is equal to the direction of the change in angular momentum. So whatever this guy changes in, it's in the same direction of the torque. Or another way of saying is that angular momentum always wants to go toward the torque right here. So here I'm talking about a bicycle tire right here. I even brought a bicycle, at least the rim right here. I did. Now, the only thing is I'm going to have to come over to this side because my handle is on this side right here. And if I were to give this thing a push right here, right there, the angular momentum, you just run your right hand along the wheel, the angular momentum is pointing out in that direction. So just remember, when you're riding forward, so if I'm riding forward, my angular momentum is riding to the left side of the bike, right here. Okay, so now, suppose you're riding and all of a sudden you fall asleep at the wheel and you start to fall over like this. You notice this thing can fall over pretty easily when the tire is not spinning. But if I spin this tire right here, you notice if I just balance this, I can just balance this thing right here. This thing does not fall over right here. Actually, right here. I can just balance this. If this wheel were not turning, if I just stop this, it just falls over right here. So what happens is when this wheel starts to, when this wheel starts to tip over, you notice it's turning the wheel this way right here. So when you start to lean that way, it's going to start to turn the wheel this way, which keeps you from falling over right here. So this is a good thing for riding bikes right here. You'll notice if you just take a coin and roll it along the ground, it doesn't just roll and fall over. As it starts to tip, it turns right here. So this is an important factor, especially when you're teaching a little kid how to ride a bike right here. You want to make sure that he has a lot of angular momentum because this is what's going to stabilize him. So you could either give him big, massive tires, or you could take him to a big hill and give him a big speed right here. Now, if the kid is just too scared, what you can do is you can take the bike up to the top of the hill and you can give it a push with no one in the bike. The bike will ride itself down the hill, all by itself. Now you take the bike back up onto the hill and you say, just sit in the seat and it will ride you down right here. You just hold on right here. No, what do? We always take them to a little parking lot, and then we say, here, go ahead and ride, and we're riding real slow, and they're really unstable, and then we say, don't hit that pole over there, and they go, what, that pole? Yeah, they'll head right for whatever you point out, so don't point out the dangers to them when they're riding a bike, because they're going to head right for it. So this right here, this thing right here, when this thing when you're starting to lean over, the torque is actually coming back this way. And what do we say? Angular momentum, which is that way, wants to go to where the torque is, right here. So one of the problems I always like to do for my previous right here is to give this problem. I'll probably put it on the final. I don't think it'll be on this next test, but at least be on the final. You have a car right here. This is a top view of the car. Here are the 4 tires right here from a top view. Here's the steering wheel, just so you knew which way the front end of the car was. So the front end of the car is over here. And mounted onto the chassis, you have a big disc right here. Okay, and I'm just going to say that this disc is spinning the same as the tires. So that means that this disc is spinning the same way the tires are spinning, so it's going around like this because the car is moving in that direction right here. And so the first thing is what is the direction of the angular momentum right here? What's the direction of the angular momentum of that disc right there? Well, if you ever want to get the direction of the angular momentum, just take your right hand, remember, just run it the way the disc is spinning. So in that case, it's in this direction right here. So it looks like it's in that direction. There would be the direction of the angular momentum. I'll even put it on there. So if we just put it over here, this L, angular momentum, would be pointing in that direction right there. Now, we come along here, and we're going to make a left turn right here. Because we're not putting a torque on this until we make a turn. So if we make a left turn, that means you're turning off like this. This is a top view. Well, there's a torque on this disc right here. The torque, you're trying to twist everything this way, right here. So you're trying to make this disc go like this. Well, this torque, you just run your hand the way the car's turning, your thumb is pointing outward right here. So there's the direction of the torque right there. What did we say? We said L wants to go to the torque. So this vector wants to come out. So doesn't that mean the car wants to twist? This car wants to twist outward right here. It wants to move like this right here. So this car, already the car wants to twist, but this is going to make it want to twist even more right here. If the tires were spinning if this disc were spinning in the other direction, so L was going this way, and you took this same turn, L would want to come this way, and the car would want to twist inward right here, which would help you because most of the time when you take a left turn, your car wants to roll out right here. But if you had a disc in there spinning in the opposite direction of the tire, the car could actually twist inward right there. So I said, well, I'll put something like that on the final right there, where all you have to do is just say the directions. There's nothing to work out. You just say up, right, left, down, whatever it is. I'll give you the directions right there. And so, but the disc doesn't have to be spinning like this. I'll give you one of 3 orientations. It could either spin like this. Oops. It could either spin like that, or it could spin like this, or it could spin like this. One of those 3. So I said, well, let's look at the other ones right here. Let's look at this one over here. Here, now let's just say the driver turns back and he sees it going, say, clockwise, the disc. So if he sees the disc going clockwise, the clockwise is this way, so he's going to see it going, he's going to see this part of the disc going in and this part of the disc coming out right here. It's going around like this. If we wanted to get the direction of the angular momentum, you just run your hand along the disc It's going in this direction. So there's the direction of the angular momentum. Now, if we wanted to get the direction of the torque, I said we have to turn the car. Well, let's turn the car to the right. Well, a right turn is going this way. You're turning down like that. So if you turn the car this way, the torque is into the board. So the torque is into the board, which means that this wants to go into the board. Remember, L wants to go to where the torque is. So if this wants to go in, doesn't that mean that you're going to put extra pressure on these two tires right here? Because the back end wants to go down, which means the front end wants to lift. So if this disc were massive enough, if you took a right turn, the front end of the car would come off the ground. And these two tires would feel the greater pressure right there. Likewise, over here, what did we say? When this one was going to the left, and we said when we took a left turn, this thing wants to come out right here, because left turn, you're coming out. So if this wants to come out, it's these two tires right here that are feeling the greater pressure right here. Well, let's look at this case right here. Now the disc is flat on the car. The disc is turning in this way. Well, which way is the angular momentum? You run your hand along the disc, so it's coming out of the board. So L is out of the board. L is out. Now I'm going to come to an uphill. If we're coming along here and we come to an uphill, that means the car's going like this, but I don't want to do backhand stuff. Car's coming to an uphill, so my thumb is pointing in that direction. So there is the direction of the torque. It's down right here. So the torque is that way right there. And what did we say? We said L wants to go to the torque. So this vector that's coming out like this wants to go down like that, which means the car wants to twist like this, which means these two tires would feel the greater pressure right here. So I'll put something like this on the final, and it's, you just make sure you get the direction of the angular momentum, the direction of the torque, and then just remember angular momentum wants to go to the torque. Here I put down one last one right here. You have another disc. I made it just like this. And I'll just say, let's say when the driver turns to look back, it's going clockwise again. So that means it's going like this, just like it was before. And so L will still be going in that direction, just like we did before. L will be going this way. But now let's say he comes to a downhill. So if he all of a sudden comes to a downhill, you're driving and you come to a downhill, you're going into the wall right here. And so the torque is in that direction. So torque, this case, would be right there. And so we said L wants to go to the torque. So here, it's not going to put any more pressure on the tires. This thing, the back end of the car wants to twist around right here, right? Because L wants to go in this direction. So if you had a downhill and a right turn, you wouldn't have to turn the wheel right, because as soon as you came to the right, as soon as you came to the downhill, the back end would all of a sudden flip around. You just keep the foot on the gas pedal. So this thing would automatically slide the back around. So this is what they do in segways and everything else to give you stability and stuff. This is what they use to calculate what's level in an airplane. They can't use a bubble level. They use these discs right here, which they call gyros right here. This is also how, if you look at the Earth right there, whenever you buy a globe, it's always tilted right here. Well, the tides are trying to straighten it up, but you notice when I try to straighten this up, I can't. It just kind of wobbles. So the Earth's orbit is actually wobbling right here. The more I try to straighten it up, if this thing is spinning fast, right here, I can't straighten it up. It just wants to wobble more. And these are really light wheels. Just think if you had a heavy wheel on there, I'd never be able to straighten this thing up. So the Earth is actually wobbling right here. And you'll notice this point points out to the North Star, and our seasons are dictated by this tilt right here. Later, when we're tilted like this, our seasons are reversed right here. Newton was able to calculate all this out. This was a 26,000 year cycle. He was able to calculate this. So in 13,000 years, the seasons are reversed right here. Also, luckily, when we were over here, we had a North Star to point to. We don't have a North Star. We're lucky we had a North Star when we needed one right here for the last couple thousand years right here. Otherwise, you'd have been lost right here. This is what they use to keep the Hubble, pointing the Hubble at different directions. They have 3 of these discs right here in 3 different directions. And by changing with an electric motor, making one spin faster, they can change the angular momentum. And remember, when you change the angular momentum, that puts a torque on the whole spacecraft, and since they have 3 separate disks for each direction, they can put a torque for each of the 3 components, and they can move with electricity. They can point to different directions right here. Normally, when you're out in space, you can't usually you need like a little gas to throw this way to move this way. But here, they can do it all with electricity since they have solar cells right here. Okay, so get this stuff down, because I'm going to put something like that on the final at least, not on the next test.